My name is Dongma, and I'm here today to present our work, SolarGest, Ubiquitous, and battery-free gesture recognition using solar cells. With the rapid developments in sensing technology and artificial intelligence, gesture has become a more natural way for human-machine interaction. Compared to touch-based interaction, gestures have inherent advantage in some certain scenarios, like smartwatch, where the size of screen is very limited, or when people are driving a car or wearing gloves. A basic step in a gesture control system is to recognize the user's gesture commands, which can be achieved by various sensing modalities like vision, light, motion, and acoustic signals, with the assistance of specialized sensors. However, all these sensors consume power during operation, which further shortens the battery lifetime of mobile devices. So to address this problem, in this work, we present SolarGest, which employs solar cell as an energy-free sensor for gesture detection. As seen in this figure, solar cells harvest energy from the incoming light and generate photocurrent. On one hand, the photocurrent can be converted into energy and to supplement the device battery. On the other hand, it can be utilized as a source signal to detect hand gestures, where the key idea is that hand movements blocks different amounts of light to the solar cell, so that the signal shows distinctive patterns under different gestures. We consider two types of solar cell. Conventional solar cells are opaque, which might be widely used in future IoT devices without a screen as a supplement battery. And the transparent solar cell is a newly emerging type, which looks like a glass, and we can just see through it. The most promising feature of transparent solar cell is that it is able to turn the screen of future electronics into an energy harvesting screen. For example, the Lunar Watch is the world's first transparent solar-powered smartwatch. However, the drawback of transparent solar cell is that it has much lower energy harvesting efficiency within the visible light spectrum, which might make the gesture recognition more challenging. In addition, when we introduce solar cell in the gesture recognition system, we actually introduce more variations or design choices into the system, like the size of a solar cell, its energy harvesting efficiency. So to overcome this challenge and fully understand how the photocurrent are affected by gestures, we develop a geometric model to simulate the gestures, the photocurrent signals using the solar energy harvesting theory. Specifically, we model the human hand and the solar cells as a round circle and define a set of parameters when performing a gesture, like the speed and displacement of hand movement and the proximity between the hand and the solar cell. Then we apply a 2D sectional analysis to calculate the amount of the photocurrent. Only the light from the green area can reach a solar cell and convert it to energy, while the light from the green area is blocked. After simulating the gesture signal, a key utility of this model is that it enables the system designers to estimate the recognition accuracy without really building a system and collecting data. In addition, with this model, we identified 8 parameters that might have some certain impact on the gesture signal, like the hand size, the angle when performing a gesture, and the environment light intensity. We categorize all these 8 impacts into a temporal dimension and amplitude dimension, which would be useful to guide our signal processing pipeline later. And the simulator code was released at GitHub. Here is the system overview of SolarGest. When a person is doing a gesture over a solar-powered device, the generated photocurrent can be sampled and fed into a gesture signal processing pipeline, including the denoising, signal segmentation to extract the start and end of a gesture and an alignment stage. Then we just use a machine learning-based recognition framework to recognize the gestures. We propose to use a discrete wavelet transformation coefficients as features and just evaluate 4 typical machine learning-based classifiers. As mentioned earlier, the different parameters have some impacts on the gesture signal, so we introduce an alignment stage to address it. In particular, we use the Z-score transformation to deal with the signal variations in the amplitude dimension and the dynamic time wrapping to address the temporal issue. Here are two signals collected at two different conditions, and we can see that after this score transformation, the amplitude of the two gestures are aligned to the same scale, and after DTW, the lag in the time dimension are fixed. To evaluate SolarGest, we manufactured two transparent solar cells with different transparency level in our photovoltaic research lab. And the experiment was conducted in a controlled environment because the transparent solar cell is not encapsulated and its performance might be affected by the environment temperature or humidity. To compare with the light sensor-based method, we also implemented two photodiodes and recorded the data at the same time. Then we designed 6 gestures as shown in the left figure and evaluate the performance under different environmental settings, like the light intensity ranging from very dark environment of 50 lux to an outdoor environment with direct sunlight of 70K lux. To evaluate the robustness of SolarGest, when one subject is performing a gesture, we ask another one to walk around within a half circle to create some artificial interference. This graph compares the waveforms of the gesture simulated using our model and collected using real solar cells. For the same gesture, we can see the waveforms looks quite similar, demonstrating the effectiveness of our model. This table compares the recognition accuracy with different classifier and different transparency level. So all the classifiers achieve good accuracy up to 96%. And for a given classifier, the transparency level doesn't affect the performance too much. When compared with the light sensor-based method, solar cells still achieve better performance because it actually acts as a two-dimensional passive light sensor with larger coverage. Our interference experiment shows that the nearby movements indeed have some certain impact on the gesture signal, but it only results in 1% accuracy loss. And the light intensity environment shows that although the light intensity varies within a large range, we can still achieve good performance. Finally, we measured the power consumption of the light sensor and found that our system can save more than 40% system power. So our method achieves good performance when the training data set is mixed with data collected at different light conditions. But when we train the model with data from one light condition and test it with those from another condition, it suffers from around 8% accuracy loss. Moreover, the problem is that it is impossible to collect the training data at all light conditions. So since our simulator is able to simulate the gestures, one potential solution is to combine the synthetic data from our model with the real collect data to improve the performance under unseen scenarios. And this is just a preliminary work investigating the sensing capability of solar cells, which opens the door for more sensing applications like device-free indoor localization. And in this work, we only consider the sensing aspect of a solar cell, we didn't practically use the harvested energy. So future research might combine the energy harvesting as well as sensing to build self-powered sensing systems. Like, for example, putting the solar cells on animals and track their activities. And at the end, I would like to show a quick video, a quick demo for a solar cell-based music player control. We use the down gesture to play the music. Sorry, the sound doesn't work, but you can see the change of this pattern. Okay, thank you for your attention. I'm happy to take any questions.